Hi everyone. We're about to start rebuilding our M54 B30 motor after taking that out to try and resolve some undiagnosed overheating problems. We're going to be starting with the reassembly of this engine, and I'm going to try to keep you in the loop with what we do. I'm going to be starting with the oil squirters, which essentially get located there, those little 6 holes, and I'm going to be assembling those into the engine now. Here we've got them over here, and I've got my threads cleaned up. They used to have some blue Loctite. I've got some new blue Loctite here. I've got my torque wrench set to 10 Newton meters according to the technical information system from BMW. And one thing just to take a look at doing before you reassemble your oil squirters into the motor is to ensure that they've been cleaned out. So these have got some kind of non-return valve or a little ball with a spring, I imagine, inside there. And what you want to do is you want to take a compressed air gun and put compressed air onto that surface there, which will squirt out all the remnants of oil and potentially some kind of, muck and grime that may have built up over the years. So I did that with all 6 of these and cleaned those out. So yeah, just clean those out with a little compressed air gun. You'll see some stuff will spray out, and then you can proceed to install. I'm going to do that right now with my torque wrench, and I'll start applying some blue Loctite to the threads of these M6 Allen head bolts. All right, we've got our oil squirters in, and now I'm installing the main bearing set. So the block side inserts are already installed here. You can see here that this part of the bearing has got the continuous journal, the runner, this gap here, whereas the other part of the bearing has got a flat surface. So that goes into the bearing cap, and these go into the block. You can see they're keyed. On this side over here, you've got a little key, and that's how you know which way to put them. There are 7 positions over here, counting from the front over here being number 1. And important to note is number 6 over here, which houses the thrust bearing. The thrust bearing is located at the bearing position number 6. Number 7 receives a standard bearing set. So I'm preparing the crankshaft now to go into our motor. I'm going to be using some standard engine oil just to prepare the bearing and the journal, and then I'll start preparing the bearing cap set, inserting the rest of the bearings into those, and then we'll look at the tightening and torquing procedure. We've got a new bearing set from KS here. Just for interest's sake, here's the part number. Alright, so the crankshaft is in. We've got our new bearing set in and torqued down. The tightening procedure is some 20 Newton meters applied to your main bolts first, and then 70 degrees. And as an added bonus, the crankshaft still turns.
Morning guys, it's a cold and overcast summer's morning, or certainly late spring morning in South Africa, and so we're pretending we're British. Nick and I've got a mug of tea each on the counter. We're about 4 weeks away now from our next race, and as you can see, we've still got quite a lot of way to go. Just to recap, we've at the last race we had the overheating issues, which we'd run out of options on. Decided to strip and rebuild the motor, but I'd also crashed the bloody car, and so we've still got a lot of work to do on that. I've prepared body panels, and I'm pretty much ready for paint on that, but that's going to be something that's got to stand down until we get this done. So about a week ago we got our bits and pieces back from the machine shop, and shout out to Precision Cylinder Head, I think it's called Precision Cylinder Heads in Centurion. Clive there has done a couple of heads for me in the past, and he's really old school, but it looks like workmanship is really fantastic. And I think what I want to start off with is just talking about costs so far in terms of what we've done here. I'll cover the cost of of the parts, the pistons, rings. It's only one piston we had to buy, but it was a piston, rings, big ends, main bearings, gasket, head gasket, etc., etc. It's all pretty much the pricing that you'll pay at any of the aftermarket guys. We happen to use BMO spares for that. They really look after us. But let's talk about the machining costs. The reason I wanted to talk about that is Nick and I have been following the 50s Kids threads for quite some time. His channel has been awesome, and he's done a very comprehensive M54 build. So guys, if there's anything that we kind of gloss over or skip on and you haven't checked out the 50s Kids stuff, please go and have a look there. He really has a great channel. But he also shared with us the price, the cost that he spent when he actually did his M54 motor. And I guess what it does go to show is, you know, we often bleat and moan about all of the downside of living in a country like South Africa with some of its political issues and its economic issues. But one thing is, we certainly have an advantage when it comes to the costs of putting these things together. So the 50s Kid spent about $1,000 on machining costs, but he did have 2 bites of the cherry, he had to replace a head and so on. And he figures that just the head work would have cost him $500 from his kind of run-of-the-mill machine shop over in the US. I'm not quite sure what state he's in. And I just wanted to compare that to what we've had done here. So firstly, we didn't only take the head in, we took the head and the block into Clive, and the block was decked. They took very little material off, but we did want to make sure that it was absolutely flat and true, because remember, we are toying with the idea of maybe boosting this motor at some point in the future, and these alloy blocks are not ideal for boosting. So we need to make sure that we've covered every base and are not taking any chances. So the block has been decked and is nice and perfectly true. Was cleaned up for us, and then we got Clive to install new thread inserts for us. So even though we tested all of the head bolts before we removed the head, and everything did take torque, we decided nevertheless to have inserts, and we put in some pretty chunky M14. Basically, it's the equivalent of the big cert, the time cert big cert. So they're in. Then, in addition to that, we then had the head work done by Clive, which was a skim. We stripped the head completely for him, so he didn't have to do any stripping. But he ground the valves. He replaced the valve for us. One of the valves on cylinder 5 was actually bent slightly, and he picked that up when he was actually cutting the valves or grinding the valve faces. He cut the valve seats. Valve guides were absolutely fine. And then he reassembled the whole head for us as well. So he basically put in the valve stem oil seals for us, which we supplied, and reassembled the valves, the valve springs, and the keepers and everything. So what did we pay for that? So bearing in mind, 50s Kid just for the head spent $500. So ironically, the most expensive part, Joe, was actually putting the time certs in. That was the equivalent of 110 US, so it cost us 1,840 Rand, 110 US dollars. The complete recon of the head, get this, $85. So basically 1,380 Rand, 85 US dollars to basically do a skim and a complete valve job on a cylinder head. And then finally, the skimming of the block, which Clive actually outsourced, came in at another 750 Rand, 45 US dollars. So I guess that's something that we can be, pretty grateful for, is that despite being, 10,000 miles away or 10,000 kilometers away from just about anything, we can get everything we need for these motors at the right prices, and we can certainly get all the mechanical work done. So that's pretty cool. So moving on to where we are so far. So what we had done last weekend is effectively reassemble the bottom end. So we got the new piston. We've put new rings on all the pistons. All the pistons were cleaned up. New big end bearings and new main bearings. But before we put everything back together, we decided to balance all of the components. Obviously, we can't balance the crank, but we did decide to check the balance of the pistons and conrod assemblies. And the specification apparently allows for up to a 4 gram difference across the range on rods, I believe it is. I'm not sure what it is on the total assembly, but a number which we did pick up off the HP Academy, the High Performance Academy's channel, was Andre there talks about balancing to within 0.1. Now, $1,000,000 question, of course, is why? You know, what's the big issue? Now, it's one of those things which is not going to help at all with performance, but it's one of those things which can possibly help with reliability. And the one thing which is often overlooked and is the downfall of every race engine is definitely reliability. So, given the fact that these M54 motors have an issue with harmonics and so on, any vibration which we can take out of it, any balance that we can introduce into it is going to be a great thing. And along with all of our thinking and every one of the decisions that we make, it's all about what is the cost to performance benefit. And in this case, the performance benefit is, let's say, unknown, but the cost is effectively zero. So we went along and picked up a little, it's basically a jeweler's scale. It costs about 150 Rand, $10. And with that, we went and balanced all of the components. And we did find, I did find up to about a 5 gram difference as it happens across the entire assembly. And once we had finished balancing, and we did manage to balance everything quite easily to within, well, not easily, it's a lot of work to grind material off, but we got everything to within 0.1. But if you're thinking that 4 grams doesn't sound like a lot across the range and a little bit of material here and there, I've got to tell you, I was extremely surprised at exactly how much material that translated into. And basically, despite the fact that we would have lost some material with the grinding process flying all over the place, but the material that we captured in the little container below where I was grinding would have easily filled a shot glass. So it's a bunch of material which actually came off to get us to the point where we were within 0.1 of a gram. So that's cool. Really looking forward to getting this thing spinning and seeing how it feels. In line with that, got the front timing cover on. Didn't replace timing chains. The reason I put this cable tie in fact, was not to stop it from falling down. But when I removed it, I just threaded the cable tie through in such a way that the point of the cable tie would just confirm direction. So when I put it back on, I wouldn't risk putting it on the back to front. I'm not sure if that would make a difference, but obviously the moment you disturb something, you want to be putting things back together the way they are. So the oil pump has gone back in on the underside, as has the little splash guard. And Nick, if you want to come in a little bit closer on the drive gear, you guys will remember we did this modification here. So our famous oil pump nut problem, we're dealing with a belts and braces approach. Red Loctite on the nut is drilled and wired, as you can see. And then further than that, if you can see down the side here, and I'm not sure with the light, you'll see that we did introduce this tensioner unit. This tensioner is borrowed from a, I think it's a Volkswagen TDI engine. Does the job just fine. And there's very little wear on that tensioner, so it looks like it's doing its job. So all good with that. And then also got the rear main seal on yesterday. Guys, if you do a rear main seal, luckily Nick had read up a little bit on this. I was just about to blunder into it and do it as logic would dictate, but it is quite prescriptive in terms of how you treat the seal and how you actually introduce it onto that rear main seal bearing face. So just make sure that you do read that stuff. Of course, the source for all of the information here, everything that we're doing right now, the most important thing in our view is cleanliness and torque. You know, if you follow those rules and you're slow and methodical, you shouldn't go wrong. And I hope I'm not tempting fate now, and we've got a nasty video to give you guys in a week or two's time. But paying attention to cleanliness and paying attention to your torque settings is absolutely crucial. And with that in mind, the source that we've been using, I think along with everybody else, has been Newtis, which is a site where you can actually access all of the technical information on the BMW family of engines, from repair procedures right through to torque values. Bad news is that about 2 weeks ago that website was taken down, and that's I think it's a pretty crappy move on behalf of BMW. If BMW are trying to lock in the intellectual property on the maintenance of 20-year-old engines, I don't think it's in the spirit of what the BMW brand is about. There are a lot of really dedicated BMW followers, and they do that because there's been a growth of competence and knowledge about BMW products, and that's come from BMW's own in-house intellectual property and information, and also on lessons learned out there in the field. So, you know, I'm fine if BMW wants to protect information on a 10-year-old engine, but you know, this stuff is old as the hills, and for them now to say, you know, you can come and officially buy access to this information at $25 for a day, yeah, it's crazy. $2,500 for a year's access. It just doesn't make any sense. So I don't think BMW have done themselves any favors. They probably have their reasons, be that as it may. But you can no longer go into new TIS and get these torque values off there. So you may be a little stuck. As it happens, I happen to have bought at some point, and I think it came with our coding cable. We got a TIS CD. So we run TIS off a PC. So we've got access to the information. I'm not sure if that was legal, if there were copyright issues about that at the time. I don't know. But yeah, if BMW wants to phone me and take issue with it, they can feel free. So what we've got now, we put the head on, and it's had its initial torque. It's 40 Newton meters on all the bolts in the correct sequence, and then a check of that to make sure that the head had decked down properly. And you need to make sure about that, by the way, guys, because your dowels can foul on the head, and your head doesn't necessarily just slide over those dowels. You can hang up on the dowels, so you need to make sure that you lightly bolt your head down through the two bolt holes where the dowels are to get it flat and seated out. Run through your torque sequence, and then run through it a second time. Make sure they're all sitting at the 40 Newton meters. And all that's done is it's just made sure that the bolt head is seated down firmly on the washer. And we're now going to go down and torque the head through the two 90-degree sequences. But I just want to quickly take a couple of moments. You know, we gain our information on how to do this stuff from the community, and there's a lot of stuff we don't know about firsthand, but we rely on the experience and the information that is proffered out there. But there are a couple of things which we are actually qualified to speak on, basically from our mechanical engineering background. And the one thing that I did want to deal with was some of the myths that surround torque to yield bolts, and why they are what they are and how they actually work. And what's prompted this was I came across a thread the other day where some guy was actually getting quite uppity about people challenging him on his views around these engines. And he was basically claiming that he'd done some tests when torquing down a head, and so while he was going through the angular measurements, he was also checking the torque that was required to achieve that, and he found a huge range of torque. And based on that, he decided to reject the angle method because he felt that this was giving an irregular or a variable torque onto the bolt. Now, this is where, unfortunately, he's absolutely gone down completely the wrong rabbit hole. He stumbled on precisely the problem, but he hasn't understood what it's about. So I just want to explain what that is all about in as simple terms as I can. So Nick, if you could just come forward a little, I just want to kind of show everybody what we're talking about. So this is a typical torque to yield bolt, and I hope you can see that clearly in the video. And what is important here is this narrow section here. Now what this is actually the bolt neck, and this is the area which is designed to yield. So just like when you pull a piece of chewing gum, the thinnest part is the bit that stretches rapidly and then will eventually break. So what is happening here is this bolt has been designed to stretch in a very specific fashion and in a very specific place. Now, just to understand how pretty much any material works, firstly, when you stretch it, it goes through firstly an elastic phase. So as you put force on the bolt and you try and stretch it, it will get longer, and then when you release that force, it'll recover straight back to its original length. And you can do that over and over and over again. Eventually you might get fatigue failure getting in, but in principle, as long as you're within the elastic deformation zone of that material, it will just recover back to its original length. Unfortunately, the force that is taken to extend something over an elastic range is variable. So the more force you apply, the more extension you get. Now remember, what we're looking for when we're bolting something, and particularly something as critical as a cylinder head down, is we're looking to clamp the thing. Okay, that's all we're looking for. We're looking tensile force in the bolt to give a constant clamping force between the head and the block. We don't care about the torque. The torque is the only way that we've had historically to measure or to estimate how much clamping force there is, but it's just about tensile force. So what happens is once you bottom the bolt out as we have now, as you then start to rotate it further, you get a resistance to that as the bolt starts to stretch in its elastic zone, and the resistance grows linearly. And it eventually will get to a point where it cannot stretch in the elastic zone anymore, and it actually starts to deform plastically. So that means it starts to stretch beyond the point at which it will return. And so if you then remove the force, it will not return to that length anymore. It will stay that longer length. And once it's in that plastic deformation zone, the force actually stays constant. And this is a characteristic which is incredibly useful where we're looking for a constant clamping force. So there will be a zone over which you can stretch and stretch and stretch this bolt, and the force will remain constant across that stretch until eventually you get to a point where you will get necking down, and then you will get failure of the bolt. And basically what that means is your force drops off rapidly, the bolt stretches and ultimately will fracture. So you've got this zone of operation, and this is exactly what the engineers have determined, because they know that for every degree or every rotation of a bolt, exactly how far you're stretching it. It's one thread length. I think these are M8 by 1, M10 by, well, M8 by 1.5, I think it is. So for every rotation, it's a 1.5 millimeter stretch that you're going to have over the neck section of this bolt. So they know exactly what that is, and therefore by rotating through 90 and another 90 degrees, they know that we're putting exactly half a rotation, or 0.75 or whatever it is, 0.75 millimeters of stretch, and that gets us into the elastic zone. And you'll probably find that it's somewhere in the middle of the elastic zone that they've aimed for. So you might find that it goes elastic at 100 degrees of rotation, let's say maybe 1 millimeter of extension, or half a millimeter of extension, and then it remains in that plastic zone for another half a revolution or something like that, and after that you will fail the bolt. So they get it into the middle of that zone, and that means that every single bolt will be giving exactly the same clamping force. So it's highly precise from a design point of view. So why doesn't torque work? Well, the problem with torque is the force that you're required to torque this thing is doing a couple of things. Firstly, it's going into stretching the bolt, but it's also going into rotating against a friction in the threads and a friction against the bolt head against the washer. And depending on how lubricated and how clean and how precisely the condition of your threads and the condition of your mating surfaces, that torque will vary wildly. And that's why that guy experienced massively different torques to achieve the same rotational angle. But it's not torque that you want. It is definitely a rotational angle. It's a stretch that you want, and that's what's going to give the clamping. So I hope that helps you guys going forward. Just if you ever second guess, luckily most of the guys on the forums are extremely responsible, even if they're not quite sure why it works like that. They all say, you know, when people ask questions about should I reuse these bolts, they all say no, don't. There's a good reason. Is because the second time you use it, you've used up a whole bunch of that plastic deformation. There's probably a little bit left in it, but there's no way of knowing without having spoken to the designers how many or how much rotational stretch or how much stretch there is in that bolt, which may allow reuse. So that's why we have to replace these bolts. Cool, guys. So we're going to proceed now with the bolting, and so talking about the rotation, we're using these stupid things. I mean, you can get them at any spare shop. They're absolutely horrible. They really are crap. And the reason is that this little bar here, you're supposed to adjust in such a way that it locks up against something, and then as you rotate the torque wrench, this thing should slide. As it happens, these things deflect all over the place. It's highly inaccurate. So definitely a two-man job, and it's a two-man job for two reasons. The job of the one man is that's the one with the muscles, and so Nick will do that, is to yank on this on these bolts and get the rotation, and it really does take some force. The job of the second guy, and that's me because I'm the heaviest, is to hold this and to stand on on this engine stand here, because otherwise you just rotate the engine stand around the garage floor. So we're going to get this baby torqued up now, and from then we're going to go into getting the cams back on and getting this thing timed. And then we'll flip it upside down and get the bottom and covered up with the sun plug, with the sun tank. So guys, hope you enjoy the video, and we'll be back shortly.